Okay, thank you very much for the invitation. And also I want to thank the organizers for having the initiative to organize this meeting. It's really great to have more double copy meetings, especially as you've seen, we're growing really fast. Okay, so today I want to tell you about some work in a couple of papers from last year with Eric Chacon and Chris White. And roughly speaking, it's about the connection between classical solutions in gravity and Twistor theory. And we have two different formulations of this that I will go over. So let me just start with the setup first. Let me just start before even getting to the twistors at all, just the spinorial formalism. And I feel like maybe for this audience, I can go quite fast over this because I think people are probably already familiar with this. So the basic idea is that instead of working with tensors and four vectors, we work with these two component spinors where we raise and lower indices with epsilons. Now, one important thing to remember that for any spinor, we can decompose it into a sum of terms, which are fully symmetric multiplied by Levi-Civita symbols. And if I have a fully symmetric object with spinor indices, I can write it as this symmetric decomposition of individual spinors, which are called the principal spinors. Now, the way to get from tensors to these spinors is just via the Pauli matrices that I've written here. And this is a well-known example for a four vector. We get this matrix, and then we know that the determinant of this matrix is just the norm of this vector. So in particular, if we want to have a null vector, we will choose a matrix whose determinant is 0. So we know that this will factorize. So we have this factorization here. So this is all very similar to the spinor helicity formalism from amplitudes. Just one thing I wanted to mention here, that one can go the other way around as well. So instead of starting with the vector, if I have a spinor pi like this, I can construct a matrix M of determinant 0, and this will correspond to some null vector via this correspondence, and this is called a principal null direction in space-time. Okay, so now we can see some actual physical objects at this stage. So in gravity, we start with the Riemann tensor. So these alpha, beta, gamma, sigma are the usual space-time, the usual vector indices, and we decompose it into spinor indices by contracting with those Pauli matrices. I didn't write it explicitly. I hope it's clear. This is what this arrow here means. And we end up with these three different types of objects. So let me first focus on this second one. These phi's here are related to the Ricci tensor. So let us assume that we are in a vacuum space-time, so the standard Einstein equation is satisfied, so we set the Ricci tensor to 0, so we throw away these guys. Lambda here is related to the cosmological constant of our space, so again, one could in principle just throw it, set this to 0, so let's work with non-curved background. So then we are just left with this basically Weil tensor and its decomposition into the psi's that appeared in the first row here. And one observation is that these psi and psi bar are the anti-self-dual and the self-dual part of the Weil tensors. So then finally, what's left of the dynamics of gravity is just to impose the Bianchi identity on this Weil tensor. Remember, we already imposed the equations of motion when we threw away these phi's, and the equations look like this. And just a bit of notation, this psi is often called the Weil spinor, which is a very bad nomenclature, I think, because it can cause confusion with supersymmetry. But if I say Weil spinor, I will mean this guy in particular here. So there is no actual supersymmetry in this talk. Okay, so this is just a setup for gravity. Likewise, we can do the same for electromagnetism. So here we start with the field strength. Again, contracting with the Pauli matrices, we have this decomposition. Again, the phi and phi bar are anti-self-dual and self-dual parts. And then the Maxwell equations imply these sort of equations on the spinorial self-dual and anti-self-dual objects. One can actually generalize. So notice we are now starting to see some similarity between the equation we had for the Weil spinor and the equations we have here for the parts of the field strength. And it turns out that one can indeed generalize these for an object with an arbitrary n number of indices. And these are just called the massless free field equations. And the spin of the field that this object describes, as you might already have guessed from these two examples that I give you, is just half the number of indices, right? So for gravity, we had 4, spin 2, and for let's say Maxwell here, we are not doing non-abelian yet. We have 2 indices for spin 1. Okay, so what is this useful for? I mean, of course, in the context of amplitudes, I think people are very familiar with how useful these spinors can be, but also in the context of more classical gravity solutions and more classical electromagnetism solutions, it turns out that writing things in terms of these spinors is very useful if we want to classify what kind of solutions we have. So let's start with the simple one in electromagnetism. So we have, let's just take one of them. So for example, this was the, let's see what I say, the anti-self-dual part. And remember, as I was saying on the very first slide, because this is fully symmetric in A and B, I can decompose it in this product of principal spinors. And then I immediately see that I can have 2 different types, right? So either alpha and beta are really different spinors, different 2-component spinors, or they're proportional to each other. So this, we call it degenerate null direction, because this has 2 different directions. Remember, I can build 2 null directions, one from each, but these will correspond to the same null direction. And you can also see in this case that the norm of this phi will vanish. Similarly, I can look at the Weyl tensor or the Weyl spinor here for gravity. In generality, I can write it as this symmetric product of 4 different spinors. However, now I can have all sorts of different possibilities. So let's see if this table makes sense. So for example, I could say, if I say all 4 of these are proportional to each other, what I mean here is that I have this 4 degeneracy, and this is called type N. Alternatively, I might have 2 of them, say A is proportional to B and gamma is proportional to delta. So this is what I mean by 2, 2. This is type D. The most general one, where all 4 are different, is called type 1. So I hope the rest of them make sense. So you see, in this case, I can really classify different types of gravity solutions. Okay, so finally, now we get to the Weyl double copy, which was introduced in 2018 by these authors. And that was the observation that if I have an electromagnetic field strength spinor phi AB, one can construct this Weyl spinor as this very simple product where S is some scalar function. And this was shown for, here in particular, it was shown for type D solutions. And these phis were of the form of this first form here, where these are distinct. There are a few other formulations where we might have a phi and a phi tilde here. And this was, this definition was further developed and shown to hold for also type N and also in other dimensions, adding mass. And I think we will hear a few more talks later today and also tomorrow about various formulations of this Weyl double copy. The nice thing, one thing I wanted to mention, so this holds non-perturbatively, but not for general solutions, of course. For certain types of solutions, it also works not perturbatively, but alternatively, one might also imagine linearizing these solutions. So some sort of questions one might ask immediately is, why does this kind of formula hold? It's not immediately obvious from other formulations of the double copy why this type of formula should be true, and how could we generalize to other Petrov types? So you see, for type D and N, as I was showing you here, these have quite a lot of degeneracy. But for example, if I wanted a more general thing like this, could something similar to the Weyl double copy exist? So to try to answer some of these questions, it helps now to go to Twistor theory. And I'm only going to give you sort of a very superficial description, how should I say, a very basic description of twistors, where I'm going to cover just what we need for the description of these solutions. Of course, I'm not going to, this is a huge subject in its own, and it has been used in the study of string theory and also scattering amplitude. So I'm not going to go into huge amount of detail on that, but basically what we need for for our purposes. So we define Twistor space as the set of solutions to this Twistor equation. So this omega here is just a usual two-component object like I've described before. And one can show that a general solution in Minkowski space is of this type. And this X here is just a point in space-time contracted with a Pauli matrix. So this, remember, is really just X, a coordinate. Then I can define the Twistor as this four-component object made out of the omega having two components and the pi having two components. And then I have this non-local correspondence between our space-time, physical space-time, and Twistor space, whereby the location of a Twistor is defined as the region where this omega vanishes. So I just solve this equation, I immediately get what we call the incidence relation, and this relates omega and pi via the space-time coordinate. Now, something we immediately notice sorry, when I write this equation is that it's invariant under simultaneous rescalings, right? So if I rescale this omega by a lambda, and if I rescale pi by the same lambda, this equation stays the same. So this means that our Twistor space is projective. So when I have an object of this kind, I can always divide or multiply by some complex number lambda. Then a point X in position space, as I was saying, defines a complex line in Twistor space. So you can convince yourself by counting the degrees of freedom. So see, first of all, we gotten rid of omega in terms of pi. So just imagine everything is now written in terms of pi. Then I quotient out this freedom. So I'm left with a complex line in Twistor space, which if we add the point at infinity is mapped to a Riemann sphere. So geometrically, all you need to remember is a point in space-time is a sphere, which we call the Riemann sphere in Twistor space. Okay, so far we've just linked between space-time and Twistor space, but now let's actually get to some fields. So it turns out that there is a very nice correspondence between these free fields that I was describing earlier and Twistor space. And this goes in the following way. So I can define a space-time field as a contour integral on the Riemann sphere of this object, where what I mean here, rho of x means that I have some function here on Twistor space, and rho of x denotes the fact that I am restricting it to precisely the Riemann sphere that corresponded to the space x. So because I am interested in evaluating the field at a particular point x, so I have to integrate over the sphere corresponding to that point x, well, over a contour on that sphere. Good, so then the nice thing about this, so okay, at first sight, it looks like we've actually made things a bit more complicated for ourselves. Like we've introduced this extra integral here, we've made things non-local. But the nice thing about this is that this object automatically satisfies this equation of motion. So we know that if I find the correct f so that I can write my space-time field like this, it's just a couple of lines of calculation to show that this equation of motion is indeed satisfied. So here by nabla here, I actually mean partial. So in the simplest case, let's just restrict ourselves to flat space and deal with solutions which either linearize the equation of motion or general solution, but linearize. So this nabla actually you should just think of as a partial. Good, so this is the nice thing, that this will automatically satisfy the equation. Good, so then just a few other things. So remember we had on the pi's, we had this rescaling freedom. So as I was saying, the Twistor space is projective. However, in space-time, we obviously don't have this, right? So space-time itself, my field in space doesn't know about these lambdas at all. So then it turns out that I have to have my my function f have a degree -n - -2 in these rescaling. So you can quickly see why, because these pi's, each of them carry a degree 1. So here I have n indices, so I have n of these pi's, the measure has 2, so I have to have n minus 2 in order to cancel this and make sure that the field itself is invariant. Good. So just a little bit more of the mathematics of this and how exactly do we choose these f functions. So remember, I was telling you for our classical solutions, we had this Petrov classification depending on the degeneracy of the spinors. So how can I recreate this from Twistor space? So there are some tricks for doing this. And okay, so let's see. So remember that we have this factorization property. So this guy is symmetric in these indices, and as I was saying, then I can factorize it into a symmetric product of these principal spinors. Okay, so then we have the following statement. If I have an n-index spinor that has a k-fold principal spinor psi, so what I mean here is that when I do this factorization, I have this psi repeated k times. This guy will vanish if I contract it with n minus k plus 1 factors of this psi, but not if I only contract it with n minus k. So hopefully you can see this from the way I've written things here. If I take this object and and something that I think should be obvious to people is that if I contract one of the spinors with itself, it will vanish, right? Because it's a 2-component spinor where the components are bosonic, and I'm contracting with the epsilon tensor. So this will vanish. So this is why if I contract this with n minus k, it's okay, because remember, I'm symmetrizing over all of these. So I can always just hit these n minus k guys. However, if I add one more, then I have no choice. And one of the xi's that I contract with has to hit one of these xi's here. So then I have to get 0. So now we will use this in the Penrose transform. So let me take a field phi with n indices, and I will contract this with m factors of this eta. So this will give me here m factors of this product pi eta. So then the statement is that if this field has an n minus m plus 1 fold principal spinor, then the Twistor function f has an mth order pole. So how to see this? So as pi goes to eta. So imagine pi goes to eta, then immediately this contraction would vanish, right? However, sorry, it vanishes, it goes to 0 as a power of m. And this f here has an mth order pole. So I'm getting an exact cancellation between the pole here and this power of 0 here. So I've basically removed the pole in this contour integration, which means that, by Cauchy's rules, when I do this integral, then I get 0. And this agrees on the left-hand side with the fact that if I've contracted m factors here and I have n minus m plus 1 by a similar by a similar argument to what I had here, this left-hand side will also vanish. So we have a direct link between the order of the pole of the Twistor function and the degeneracy, i.e. the Petrov classification on the space-time. Good. You can stop me at any times if you have questions, by the way. So now finally we get to the Twistorial formulation of the double copy. So remember, we had the space-time type D Weil double copy written like this. And now let's consider two holomorphic Twistor functions f of homogeneity -4. So remember, the homogeneity dictates the spin of the field, and for a scalar it's -2. So remember, it was, maybe I go quickly. So it's -n -2, where n is twice the spin of the field. So if my spin 1, I would have -4. For spin 0, I would have -2. So this is exactly -4 is for the electromagnetic field, and -2 is for the scalar. So this will necessarily correspond to these guys in space-time. But then it turns out that I can form a product in Twistor space for gravity as well, which looks very similar to the one in space-time, and immediately I see that this gravity guy has homogeneity -6 because I've put together two -4s, and then the -2 is in the denominator, so that cancels it. So this is homogeneity -6, so it could correspond to a gravity field, and then one can show explicitly via a Penrose transform that indeed it does. So this gives the type D Weyl double copy in space-time. Okay, so we can actually do it more explicitly here. So remember, I was telling you the order of the poles that we have in the Twistor function is related to the type of fields that we have. So we can actually define the simplest version is to define this family of Twistor functions in this way, where to get here we've used this relation between omega and pi when we restrict to a particular point in space-time, and here I've used the fact that Twistor space is projective to choose a set of coordinates to describe this object. And then the idea is that I can carry out the Penrose transform to get these objects in space-time. So you can see explicitly that these guys that we've constructed here reproduce the type D Weyl double copy. And one thing I wanted to mention is that this actually opens the door to having a formulation in curved space-time, although we haven't explored that much because the Penrose transform itself works for conformally flat space-time, so not just standard flat space-times. Another reason why it is useful is because it allows us to go beyond type D and type N and write something more general. And this is because of this simplification property that it has of allowing us to classify things in a different way. So let me show you, okay, this slide is a little bit loaded here, but let's see if it makes sense. Let me show you how one can generalize the Weyl double copy to get type 2 gravity solutions in the Petrov classification. So you can look at the bottom of the slide first here to remind yourself. So type 2 means that I have 3 types of spinors here, and one is double degenerate. And it turns out that one can do it explicitly by starting first with 2 different types of electromagnetic twistors for electromagnetic fields. So one, this thing I called 0,2 will give you the degenerate version, and the 1,1 will give you the non-degenerate. So curly A is different from curly B here. And you can see this by looking at you can convince yourself if you're curious later by looking at this basically tells you what kind of poles I have, the order of the poles, and you can see how the order of the poles is related to the degeneracy here. And then for the scalar, I just choose this simple one here, and I get this function. And then it turns out that you can construct the Twistor representatives for type 2 solutions using via this formula. So this is still in Twistor space here. So this is type 2. It's a sum of products of the Twistor functions for the electromagnetic ones, and then always divided by the scalar guy. And then in space-time, this becomes, so these CA and AB, you can just think of them as some constants to set to the side. You can ignore them, but you can see that this psi becomes a sum of products. So this is slightly more general than the standard type D version of the double copy, so which was basically just one product and then divided by the scalar. This is a linear combination of 2 products. And here I have to say that for type D, we're just assuming that we're linearizing. So I'm always assuming that these solutions satisfy a linearized equation of motion. So either I'm able to choose coordinates, which I think for type D, we don't generally know how to do, so then one has to linearize by hand. And then indeed one can see that you can get this more general type 2 version. And we've actually shown in the paper that you can do it for type 1 as well, and it allows this generalization. And so the point is that the Twistor language reduced the problem of reduced us to the problem of finding combinations with the correct pole structure. And remember, when I was showing you this Penrose transform, these are then guaranteed to satisfy the equations of motion. So somehow the sort of differential equation part of the problem, where one has to check that these guys are really solutions, is removed in this formulation, because we can directly just look at the algebraic properties of these functions. Good. However, this is still a very new field, and we have many things that we don't fully understand. So let me show you one of the problems that we initially had and one of the solutions that we gave to this. So remember, we had the Penrose transform that I've defined in this way, and now I've even given you a little drawing just to make it a bit more concrete. So this gamma is a contour on the Riemann sphere. Now, it turns out that I can modify. So first I was just telling you that this f is some kind of function. However, it is not a simple function, because it turns out that I can add to it. So imagine I have this contour and I close it such that I'm looking at the north part. Then I can always add to it a function which has singularities, i.e. poles, only in the southern hemisphere, right? So you can see immediately that when I'm closing the contour and looking at the north part, this integral is just going to give me 0 for this contribution here. And then similarly, if I look at the south part, I can choose things that only have singularities in the other part. So I can always add things, and these guys are obviously not necessarily 0. They can be valid functions. It's just that in the first case, they don't have any poles in the northern hemisphere. However, then when I integrate, I get 0. So from the space-time perspective, I don't see these guys at all, right? So the problem that we have now is that this is not respected by the double copy that we've defined. So if I look at, let me show you the simple version of just so you don't get bogged down in the details, but if I look at this version of the double copy, you see that if I add here, these guys all have poles, right? Both in the northern and the southern hemisphere. So if I add something, if I add a term here that doesn't have any poles, it should not affect the gravity guy either. However, unfortunately it does, because when I multiply it with the other guys that have poles, it will give me physical contributions, which is not which shouldn't happen. So then one has two options. Either we have a way of formulating the double copy in Twistor space that's invariant under this, and that's a very interesting and open question, I would say. But for now, what we've resorted to is a simple thing, and we have just asked how we can basically gauge fix, quote unquote, this freedom that we have here. So how can I choose canonical representatives such that I don't have to worry about this freedom? And to do this, we actually have to go to a different formulation of the Twistor double copy, which is called the Dolbeau double copy. This was a Czech version, by the way, that I was showing you earlier. And the Dolbeau, it turns out, is actually the one that's more used in contemporary research on twistors. So I'll give you again just the very basis of the Dolbeau setup, unless there are any questions up to here. Okay, good. So let me just be, again, very schematic. So on a complex manifold, these are just some very basic reminders. So, we can define PQ forms by separating into the holomorphic and anti-holomorphic part. So when I say I'm writing a PQ form, I mean something of this form. I have these Zs and then these Z bars. And then going to Twistor space, we define what we call the Dolbeau operator, the partial bar, in terms of these conjugate Zs. Remember, Z was the 4-component twistor that I was showing you earlier. And of course, I could have defined an unbarred version as well. The reason why I chose the bar one is because we can use it to define holomorphic quantities, right? So when partial bar of H is 0, this we say is a holomorphic object. And it also squares to 0, so it's also nilpotent. Good. So now in this formulation, this is the Dolbeau version, I have, again, the Penrose transform I was showing you earlier can be reformulated. And you see, it looks very, very similar. There are just some subtle differences. So on the left-hand side, I still have the space-time field of spin n/2, as I had before. The first difference here is that instead, so remember here, I was integrating over contour gamma on the Riemann sphere. Now I'm integrating over the whole Riemann sphere. So now, because I'm integrating over this whole manifold, this object here should be a top form on this two-dimensional complex manifold. So what I should have here is a 1,1 form, basically. And notice that the measure itself is a 1,0 form because of this d pi. So then we find that the Twistor representative in this case, f of z, is actually a 0,1 form, is an anti-holomorphic 1 form. Again, we have a very nice result that if this f that I have here is closed, then the Penrose transform ensures the equation of motion for phi. So again, as before, one doesn't have to worry at all about the equations of motion in space-time itself. Those are just ensured by the fact that I've chosen this guy to be closed. Again, we have this redundancy. So remember here, we had the redundancy when we had an absence of poles in the north or south hemisphere. Now we have a redundancy that actually looks a little like things you are familiar with from gauge theories. And that's it. If I add a partial bar g to this f here in this integral, one can show that if partial bar g is globally defined, and this is something important that we'll see in the next slide, what I mean by globally defined, then the partial bar g will vanish under integration, so will not contribute to the space-time result. Good, so what we say then is that f is an element of the Dolbeau cohomology group, which is a quotient of closed forms by exact forms, and it's a 0,1 form. So let me know if any of this doesn't make sense. So that's just a definition. Good. So now, remember we had a double copy formulation on in the Chach version. It turns out that we can translate it immediately to the Dolbeau version. So this is the first type of double copy that we will write. And so it turns out that on the local patch of the Riemann sphere, one can simply start with Chach representatives, hit them with the Dolbeau operator, and these guys will be good Dolbeau representatives for the same space-time field. And here I just did it locally on a patch, but then one can extend by patching together. You can do a partition of unity and gluing the patches together, and one can do it for the full Riemann sphere. And then it's maybe just like a few lines to prove that these representatives are again good representatives, but now working with this Dolbeau version of the Penrose transform. Now, something that a subtlety here that you might find confusing. So remember here, I was saying that I have this redundancy when I add something that looks like an exact form, an anti-holomorphic exact form. However, remember I said that partial G has to be globally defined. So these guys, even though they look like naively like sort of pure gauge terms in these formulations, they are not. And this is because of these check functions I write here, they actually have poles, right? Remember by definition, they had the right pole structure. And when I hit them with this partial bar, I'm not going to give you the details in the Twistor angle, but just remember from sort of complex analyses that this sort of operation is proportional to a delta function. So these functions here, despite the fact that sort of naively presentationally look like exact forms, they are really not. These should be part of this part of F. So hopefully that's not too confusing. It's just how they are constructed. Okay, so once we have this map, it turns out that, you know, the double copy that we had in the Chach language, the first sort of naive way to translate it to Dolbeau language is to again form the same product of the electromagnetic representatives, divide by the scalar, and then hit it with a Dolbeau operator. And this works sort of by construction because the other one worked as well, and one can check as well. So this can be done, and then in the paper, if you're curious, we see a wide set of solutions that this works for, and it's quite nice. However, the issue that I've shown you before, in that I don't know how to choose the representative canonically, is also inherited. So this freedom that I have here is not a freedom of the double copy formulation. So how can we make a canonical choice for this representative? And this is the last thing that I will show you. So one solution that we have, it turns out there are a few different solutions, but one solution that we presented in our paper from December is actually using an old formulation of Woodhouse from 85. So the idea is to work in Euclidean signatures, just that there we know better how to define these things. And I just want to introduce this conjugation relation, so you know what I mean when I write, when you see pi hat here, this is what I mean, where bar is just the standard complex conjugate of the components. And it turns out that in this formulation, the Dolbeau operator partial bar, which remember was z bar partial z bar, can be written in terms of this specific basis that's built in terms of these pi's and pi hats. And the nice thing here is that when I restrict to the Riemann sphere to do my Penrose transform, only the first term in the expansion, so only E2 survives. And how to see this is that when I have this Riemann sphere, I can think of the pi's as coordinates on this sphere, right? Pi and pi hat as coordinates on this Riemann sphere. And the Riemann sphere corresponds to a fixed point x in spacetime, so just one point. And then this basis I have here is actually for the full Twistor space. So this element where I'm taking dx, so changing slightly the position of the spacetime point, is actually not seen at all. It's actually just dropped out when I'm restricting to only the Riemann sphere. So I'm only left with this simpler formulation. And then in this version, it turns out we can choose a unique representative. So now, just like to remind you quickly, another thing that you're probably familiar with, on a compact manifold, we have, so here we are working on the Riemann sphere. Now we have this Hodge decomposition for any forms, where we have so now because F is anti-holomorphic, I have bars on everything here, right? So I have the exact, the coexact part, and the harmonic part, which satisfies these equations. And so it has these three terms, and this is a unique decomposition, is an important point. And then I remember that I said that I want F to be closed. So this was one of the first things that I said, which ensures the equations of motion. So because F is closed, I can imagine hitting this whole equation with partial bar here, and it gives me 0. Of course, this vanishes immediately when I hit it with partial bar because of the nilpotency. The harmonic guy vanishes by its properties, and I'm just left with this object. But then because of the positive definiteness of the inner product, it turns out that this part actually has to vanish for an object which is closed. So this guy goes away. Then I impose, but then I still have some freedom in the definition of F because I have these two terms. But then I can impose the following condition. And you can really think of this as a type of gauge fixing for this freedom I have here. So really can think of it as a kind of Lorentz type gauge, but in Twistor space. So if I impose this condition, then by an argument that's very similar to the one here, it turns out that this part now has to vanish. So I'm really left with F just being the harmonic part. So I found a unique way of choosing a representative, so I don't have to worry about the freedom that I have in this description here. Okay, so this was how to choose. Okay, so now we can actually be a bit more explicit. So this was very abstract. This was sort of just saying that in principle one can do it, but it turns out that one can actually do it explicitly. And this was the construction that we found in this old Twistor paper. And now the construction somehow goes the other way around. So actually we start with a space-time field itself, phi. And the first step is to construct some kind of Twistor function that I call phi here in the following way. So I just contract all the indices with these two components guys here, and then I have some volume element type thing in front, and this depends on the spin of the field that I'm looking for. And then we can construct a 0,1 form f phi just by hitting this by hitting this phi object here with this partial hat operator, which notice this is slightly different from the Dolbeau operator because we have a d pi hat here, but this is a partial pi. So we just call this partial hat, and then I get this f guy here. And it turns out one can show that this f is a good Twistor representative for the types of space-time fields that I'm looking for. And it is harmonic, so one can show that it satisfies this condition, and hence it is also a unique choice for the Twistor representative. And then it turns out that one can define a different version of the double copy, which this one now follows somehow very immediately from the space-time double copy, where I put together these phi's here, and you can kind of see it by just by eye already, that if I put these guys together for electromagnetic fields and scalar fields, if the phi's themselves satisfy the Weyl double copy, then the whole thing, when I hit it with a partial hat, will give me a gravity representative which satisfies this. So this then is a different way. So this is more of a proof of principle that one can indeed choose a unique way of defining this double copy. And what's quite interesting here is that note that this version of the double copy is actually quite different from this version here, even though they look very similar. If one just looks very naively, remember that this partial bar here is actually very different from this partial hat. So they're defined very differently. And then the component guys that go in here, these phi's that go in here, are the ones constructed here. They're very different from the F's we have here, which were inherited from the Čech description. However, when I think about what they give me on the space-time, it turns out that putting in the same, they basically both correspond to the same double copy in terms of the physical fields in space-time. So we found that quite curious. We don't fully understand yet the connection between the two, but we thought it was quite interesting that we found two different versions. It could be that there is some sort of Twistor gauge freedom connecting them, but it's not immediately obvious why they should both work very nicely. And then it turns out, so maybe I should try to finish them, but it turns out that very recently there have been some other methods still for defining double copies in Twistor space. So one is from a paper from late last year, is when they were trying to construct purely radiative spacetimes. And here, a very nice way of fixing a Twistor representative uniquely was using this characteristic data at null infinity. And this had been observed a while ago, but recently it was used for defining some very nice double copies for radiative spacetimes. And also even more recently, I think there's another version which links with scattering amplitudes. And I think later today, we will see a talk on this exactly. So by now, we seem to have maybe 4 different ways of fixing these things. So we don't yet know necessarily how they are connecting, but that is something to look at in the future. And because I'm trying to keep to the 45 minutes, I won't say much more except two kind of directions for future work. So as you've seen in all that I've shown until now, as is often the case when we look at exact classical solutions, we were working with Maxwell fields, but something that the Twistor theory might allow us to do is incorporate in this story some the non-abelian non-abelian gauge theory. And this could be done because in the Twistor language, there's something called the word correspondence, where we start with self-dual, but this time Young-Mills fields, so non-abelian gauge fields. And then there's a nice expansion around that self-dual sector to go into the full theory. So that is one option. Another natural question you might have is if there is a connection to one of the many other versions of the double copy. So I've presented here a very specific ones for classical solutions, but I think one might wonder, and it's very possible that, of course, in the amplitudes case, this has been studied. But I mean, for example, with the convolutional double copiers, they're looking at Lagrangian, etc. Could it be connected with this? So because I think I am approximately at 45. If I was, maybe I will stop here. Thank you.
Thank you very much for a very interesting talk. Do we have any questions from the audience?
I have a question. I was wondering, it seems like this would be really natural to generalize for like different spins, like higher spin things. Has anyone thought about that, or like classical supergravity or something like that? Have you thought about this?
Oh, yeah, no, that's a very good point. And unless I'm mistaken, if you mean specifically in the Twistor formulation, I'm not personally familiar with anyone having looked at it. But of course, I mean, that's a very good point, because
I mean, everything you wrote down had like arbitrary spinor indices, right? So yeah.
Exactly. So in principle, that's a very natural thing to try. And we have to admit, we didn't try it because we were sort of focusing on this gravity story where we had, the space-time formula to compare against and check that we're doing things right. But I think, that's definitely a direction to look into. And in terms of the SUSY, that's another thing that should definitely work. There we've looked, I don't think it's in the paper, but we've looked a little bit when we were looking at various examples of for the double copy here, and we were looking at plane waves, and we were looking there actually at including SUSY as well. So at least for those simple examples, definitely one can add SUSY very easily, but it would be interesting indeed for like a more general supergravity solution. And I mean, obviously Twistor's theory definitely can cope with SUSY, and it has been formulated with SUSY. So I think that's definitely something to look at, but we haven't yet. So this is all sort of recent stuff. So, but that's something interesting to possibly look at.
Great, thanks. Thanks for the nice talk. That was great.
Yeah, thank you.
Any other questions?
Yes, I also have a question.
Hi.
Hey, thanks for the very nice talk. So it's a question related to the two types of the double copy that you showed at the end in the Dolbeau case. So you mentioned that it's not clear why both give you the same double copy, basically. So are you expecting that they're supposed to be in the same cohomology class, but it's not clear why they are? Or can you check, like, at least if your scalar in both cases are in the same cohomology equivalence class?
Yeah, so in terms of the cohomology class, they are definitely in the same class. So that we know for sure, because the cohomology class tells you how your space-time field will be ultimately. So they're definitely in the same cohomology class, because we know that we get the same things in space-time. The difference between them is which representatives of that cohomology class we are picking. So let me actually go, where was I? Right. Let me show you the simple one so we don't get bugged with the, maybe the Dolbeau. So here we have picked some representatives that are kind of, they're somehow natural, because in the Czech language, we just started with what people have written in the past naturally for these types of solutions. And then somehow perhaps we got a bit lucky as well, but somehow maybe this is like the minimal way of writing it. We have to admit we don't fully understand, but that worked very nicely, and it matched with the type D very nicely. And so this is one type of representative, or in Dolbeau it'll be written like this. And then the other one that I was writing with these partial hats here, these guys are, so if I take individually each of these guys, they will be the same cohomology class, And so therefore they must be related by some of this Twistor gauge symmetry, or maybe I shouldn't call it gauge symmetry to not confuse people, but you see what I mean by this
Yes.
freedom in the in defining the Twistor representatives. But we don't understand why specifically, you know, these two guys work. And you'll see some more examples later on as well of other ways of fixing it, which also work, because we've definitely tried to take, sorry, let me go here. We've definitely tried taking more general, so I can add to this F some more general freedom, and then it doesn't work. So then it does break down, right? So if I try to very generally add to this F hat that I have from the chat, it's full freedom, it starts to fail then, right? So there's some restricted freedom, there's some.
So it doesn't work for any representative.
That's the point, yeah, that's the issue. And this is the issue with the canonical choice. And this is what other people as well have been trying to do here with the choice, is that we have a restricted family of representatives that make it work, but not the full one. Yeah.
Okay, thank you.
That's the, and something that I didn't maybe emphasize enough is that I think it is possible to try to be more ambitious, and maybe there's a more general formulation, which is not just this product, but it could be maybe some other type of product which can deal with this full freedom. But we are still at, you know, very early stages of this Twistor double copy. So I'm saying it's possible in the future, when we better understand, we no longer need to make choices, but we will be able to be. That's the kind of hope. Yeah. But thanks.
No, thanks.
Any other questions? Okay. Actually, could I ask a quick naive question?
Sure.
Instead of factoring out, instead of factoring the spin 2 into 2 spin 1s, could the spin formalism be used to factor out spin 1 into spin halves? Well, because I mean, I think you had a paper at some point about factoring n equals 4 into 2 n equals 1 Carl multiplets.
Yeah, that's a very good question. And I guess this is a little bit related to what Kara was asking earlier as well, right? So I think, yeah, no, that's a good question. And I think in principle, the answer is yes. And let me show you where I was giving the, perhaps you can see it a little bit here already. See, when I was giving the, okay, so I don't know how we would incorporate the scalar. So I guess there's a question here. So you see, naturally, already every symmetric thing has a natural sort of, it breaks into these spinners, right? And for these guys, these I could think of these guys as spin half objects. And then I guess the question is, what type of double copy do you want to have? So if you want to have something that mimics the Val double copy and have dividing here by a scalar, which we know generally from amplitudes one has to do, I think one would have to think a bit about how it would work. But I think in principle it should be something doable, yes. But we haven't done it explicitly, yeah.
And another, I mean, earlier you alluded to possibility of generalizing to a nonlinear case. I mean, so can you do, this is just my ignorance of literature, are there attempts in literature to do anything similar to, like, or try to double copy the ADHM construction to gravitational instantons or something?
Oh yeah, so there are constructions, yeah, good. But are you asking in terms of the, people have definitely looked at instanton double copies in the in space-time. And then separately, I know that Twistor theory has been used to help classify all possible things. I think this is what you're alluding to, right? It really helped with this. But I don't think the two have been connected in the sense of using both twistors and C. And that is definitely something, because those are self-dual solutions. And this is what I was saying here, that the first step when going to non-abelian is to look at this self-dual sector where you do have these instantons.